Okay, hello everyone, and welcome to day 3 of the Oh What a Lovely Molecule workshop. Today we're going to be talking about molecular excitation modeling. We have Michael Busch and Malcolm Gray. Um, our introductory slides, we're getting low on people who still haven't done their introductions, and it looks like it's just Malcolm that hasn't. So let me share my screen, and Malcolm, you can introduce yourself. There you go. Would you like to introduce yourself? Oh, he's frozen.
Hold on. Yeah, yeah.
There he goes.
So
There he goes.
yeah, um, yeah. So for many years, I worked at the University of Manchester on modelling various molecules, often with maser emission. Uh, I guess the molecules I've worked on mostly are SiO, water, OH. Um, I also studied polarization, which is the topic of today's talk, really. Currently in the Atomium project, which is a study of AGB and red supergiant stars with ALMA. I've still got some radiative transfer projects going, although I'm now sort of retired from Thailand, although I've still got the association with that institute. And I wrote a book at one point. Then there are some old models here from years ago that I put in. I was studying W75 North, I think, with Boozaba. Yeah, I think that's it, really.
Well, thank you for that.
Thank you. Is that good?
Yeah, that was
Yeah, that was
about an echo, I
got
think.
an echo, I think. Oh, is that my microphone set?
Don't worry about it.
Don't worry about it. I'll just.
Could you maybe mute
Could you
yourself?
maybe mute yourself? Yeah, I can mute for the moment.
Cool. Thanks. Okay, so let's dive right into it. We have Michael is going to talk to us a bit about Molpop, and then we'll hear from Malcolm.
Yeah, okay, so let me see. Let's see if I can share. So this talk is less of a talk and more of an advertisement, call to action, if only for myself, and just advertising the Molpop SEP code, which is a line transfer code that I spent the summer trying to apply to OH with some success. It's unpublished. And the people I worked with in this effort were David Neufeld at Johns Hopkins and Arsha Jacob, who's now a professor at University of Cologne. And we were interested in trying to figure out, with all of our OH observations and even using OH with Sophia, if we can use a code like Molpop to get the physical conditions of the gas provided the observable constraints, which is, um, kind of the name of the game. Sometimes it's hard to do. So Molpop is a code that I think I cite this 2018 paper, but I think it's even has some older citations. But the Molpop paper that is most recent is 2018 by Andreas Ensenio Ramos and Moshe Elitzer. I think first, yeah, okay, so I've written here. First written by Moshe Elitzer in Fortran 70, ported to Fortran 90. And then Andreas wrote a C++ wrapper, I believe, for it, which is its current version on the GitHub. And then I've written some type of Python wrapper that you can run in a Jupyter notebook. So there's many wrappers. It's a code that's very fast. That's wrapped multiple times at this point, but it's very fast. But I think there needs to be more development in the widespread usage of codes like this, so that we can just sort of add it to our papers where we have these observations, and then a lot of us just say, this looks like LTE, this doesn't look like LTE, this is anomalous, we're not sure why. Then these codes have a lot of free parameters you can kind of tweak to maybe like you get a grid of models that look like your observables, but it still has some problems because it's a really unconstrained problem. So yeah, so MoPop. I say up here that the anomalous conditions of OH, as we've talked about this conference, it's widely anomalous in the satellite lines, especially stage and other molecules demand non-LT excitation modeling, and the modeling of MoPop is solves the level population equation in statistical equilibrium, so it tries to figure out all the radiative transfer effects. So there's no chemistry involved as far as I know, but does rely on collision rates that are still an active topic of research. Just figuring out the collision rates of OH by H2, for example. It's a recent publication in 2020, and then Paul Degdigian at Hopkins, David and I convinced, hey, can you look at OH again with collisions with just hydrogen atoms alone? Because we thought that might be pretty important in the just very diffuse ISM where the gas is primarily atomic, and he did that for us, which we were very grateful. So yeah, codes like this, you can tweak things like the dust contribution, the external radiation, like from synchrotron radiation. You probably don't want to tweak the CMB radiation, but and MoPop also considers line overlap. I know some codes don't, so line overlap when particular irradiation from one levels can leak into the other one. And there's the GitHub code for the MoPop that Andreas has currently. So that's without the Python wrapper. So my plan is, I haven't done it yet, is to basically take the version I have that has the updated collision rates for OH and put them on GitHub with my particular Python setup that I can distribute to people at the conference. Yeah, so here I just show, some things I would like to model with MoPop. You have MoPop can also model the brightness temperatures of CO. CO is one of the molecules involved in the base code. So if we have, brightness temperatures of OH and CO, we have 4 lines of OH, maybe 1 line of CO. What constraints can we get from the models? It may not be very well constrained, but we do know that for the outer galaxy, the synchrotron temperature is pretty low. Maybe the ionization rate is just the interstellar radiation value, and the interstellar radiation field is maybe just the interstellar radiation field. So, things like this. So there's a lot of assumptions that will go into the particular modeling. So I haven't done anything like that yet, but there are some examples in the literature, including Anita's paper that used, I believe it was Molex for Mark Wardle. There's another expert who we wish could join us, but I think he's busy somewhere. Yeah, so I'll just go from top to bottom. There's this very typical paper by Ibisawa and company, where they used a code like this, non-LT modeling to use the 4 OH transition lines sort of as a temperature gauge in a cloud. And I think Anita and I have problems with this paper because their assumptions can be kind of extraneous. But you can see here that they can predict like brightness temperatures as a function of gas temperature and column density, which is nice. I mean, it gives you at least some idea of where you can see here where the solid line on the left is 1612, where that is predicting a negative brightness temperature, right? So we see this commonly in the ISM where the 1612 is in absorption. And you can see here in Anita's plots the region of parameter space where the satellites are inverted, say. And this is just for a particular set of models for varying volume density, gas temperature, etc. And then Arsha did some work too recently using MoPop, actually using my Python wrapper to model the CH ground state 3.3 lines, I believe, with Effelsberg. I could be wrong. I think it might be Effelsberg. But anyway, so that was a nice application for CH. And then I use the MoPop in my Python wrapper just to recreate the results of Ibisawa 2018. So I have a little Jupyter notebook that does that. So it was a summer doing that, which was nice. Yeah, very proud of this particular plot. It's a very grad school plot, but Yeah, and I want to come back to this and apply it to now all of my observations, and fit this sort of stuff. So hopefully this is like a call to action for my own willpower I do want to, if people are interested, if I hear more interest about this, this is the thing I should do, I will, do it. So it's kind of advertisement for this code and to force myself that I should do this. So yeah, Molpop is a fast analytical code for multi-level line emission. Here I just show some applications of OH. Here's another plot of the excitation temperature of particular lines, and for a variety of parameters that I listed at the top there. And this is just one run. Molpop is incredibly fast, so I have hundreds of files with many different parameter names that I have to figure out how to plot them and fit them and interpret them. But yeah, that's basically all I have. Let's see. Yeah, that's all I have. So if you have any like questions about how the code works or things like that, I insist you ask Malcolm. But if you have any questions for just what I presented here, that's fine too. I'd be happy to take them.
So how many levels do you use?
Oh, I hear an echo. I don't know off the top of my head, but if you go to Anita's paper, I know at least the levels involved in the pumping of the 70, 20, 16, 12 lines are modeled. So I think it does most of the rotational ladder. Then you can print out only the ones that you're interested in. So which is useful. But I don't know off the top of my head. I would need to look at like how far up the ladder they go. But it was interesting. We did adjust the far IR radiation SED. We had to like look at a recent CMB paper and see what they had for that for the 120 micron OH lines, because that did seem to be important.
Well, yeah. So, I mean, I guess that these new collision rate coefficients are very useful, but I don't know how sort of complete they are, or what rotational level they go up to. You'd know more about that than me, I think. The ones I used to use, well, pretty old now.
I see. Yeah. Yeah. The old reference was the offer rates. I don't know.
Yeah, that's right. Yeah.
Right.
Yeah.
I think the class rates are just as good. Or like they cover as many levels. But I would have to check.
Joe, you have your hand up?
I do. I have a really quick question inspired by Malcolm's question. Do you include, is there electron collisions in Molpop?
Great question. As far as I know, no. And this actually, if you go to Arsha's paper, there's some discussion about this, that she did a quick like back of the envelope calculation, I think using like the Born approximation. It's like, what would electron collisions do? And I don't remember the conclusion off the top of my head, but I think the idea was that that would be a nice thing to include, but it didn't drastically change things by orders of magnitude.
Anita may recall better, but I would think that Mark Wardle's latest implementation of Molex did include that. But anyway, this just underscores in my mind the importance of us all getting together and actually running some kind of some benchmarking tests on all of these different codes to behave. It's been on like we've been meaning to do this for ages. So.
I recently saw a paper on collisions of OH with helium.
Oh my God.
Too, and I was like, oh my God, I guess we really need to get on with it. But yeah, but Molpop, I was looking at the manual the other day and I was like, oh, it can include up to like 8 collision partners. And I was like, well, there's room for things to throw in there.
And that was my like pre-question. And then I had a quick question. You said you'd reproduce the Ebisawa results and they looked a little bit different. Are you aware, like, what's driving the differences? I know that slightly different things may have gone into it. But...
Yeah,
Is this the like exact same setup?
it wouldn't be the exact same setup. I think Ubisao uses the offer rates. I use the cost rates. This weird kink here, I'm not sure what that is, if that's computational. The axes is also a little bit different. So
And
I
in terms of
go to
the physical
one.
setup, like, did you put the
Oh, in
same?
terms of
Yeah,
this, I believe it's the same, but it may not be. This is from a
it's
few years
quite
ago right
different,
now.
mate. Like, I know that there's always
Like
ways
the
to kind of
shape.
tweak. No, even the values, right? Like the TB is way different.
Oh yeah, the TB is way different. Yeah, in
And
that case, yeah, you're
yeah.
right.
I mean,
Then some of the settings must be off. I don't know which ones.
yeah, I mean, even the qualitative shape's quite different. Like there's really like 1720 is almost flat in yours, whereas with theirs it has some like diagnostic power, you know, like in yours it sort of doesn't have any diagnostic power to tell you that
Yeah.
because it's the same.
Yeah, I suppose you're right. I was just very happy that they kind of did this whole crossing
Mm.
mechanism at sort of at, well, mine occurs at 80 and theirs occurs at like 60. So there's
Oh
definitely
yeah,
differences.
yeah. Yeah, no, I mean, I know there's any number of ways you could probably drive these. I just wondered if you had any
Yeah.
insight what they were.
I don't have any insight right now, but they're definitely they're different then. Yeah. I use the recreation as in I looked at this and I was settled enough that it wasn't there's a lot of effort to make the spot even look semi reasonable.
Thanks.
Yeah, but it's definitely not published anywhere. I would definitely need all the details are just scrambled in a Jupyter notebook.
Allison?
Yeah.
Hi, yes, thank you. No, I just had a quick comment that I also started toying with Molpop a little bit for modeling non-LT ECH. And since it doesn't include electron collisions, I actually talked to Andres about it, and they were willing to try to create an input file for that. So they haven't done that yet that I know of, but we need to kind of reconnect and see. But that was something that, I mean, I wasn't even convincing about it. Like I couldn't convince them that I really needed it. I just thought that I would need it. And so they were really helpful about it. So they were also, you know, the authors were super helpful. And if somebody does need electron collisions included, I'm sure that if you reach out to them for OH, for example, they would probably do that. I mean, OH and CH, which we will do that a lot, right? People will use those frequently. So
can you write maybe their contact in the end affiliation in the Slack channel? Because I didn't catch the name. Yeah,
I will get that and put that in there. Absolutely.
Okay. Well, that was my short little bit on Molpop. So I think maybe if Friday, if I'm not talking about diffuse OH, maybe I will spend some of the new project time on this to hopefully have a deliverable. And this is the Molpop SEP on GitHub. Apparently updated last year, which I didn't know. So I'll have to figure out the details.
Seva?
Yes. Hi everyone. Really nice talk. Just a little commercial that I will be discussing some of the results using Molpop and Radix to model high excitation OH at 5 gigahertz, 4 gigahertz, 6 gigahertz in a project that I'm working with Wei Xiantang. So that will be the next session.
Awesome.
Malcolm, you had a question?
Yeah, so are you mainly going to model this, the sort of conjugate effect in the diffuse gas with, you know, with the 1612 and 1720, sort of one inverted and the other slightly in absorption, or are you trying it on star forming regions as well?
So my hope was to do it in the diffuse gas, especially like when I look at profiles from Splash towards the inner galaxy, like with Joe's giant survey with Parks. There's a lot of conjugate absorption and even like the regional Crutcher cloud is just, the entire cloud is anomalously excited in 1720, which is like, I think is really interesting. It must tell us something about the physical condition. So if we can get a sense on that inversion in the general ISM, maybe that could be a tool. But yeah, I don't know. I just think generally it would be useful to have at the end of our papers, like, here's all of our observations, here's what it might mean about the physical conditions of the ISM. Maybe, yeah, maybe the major people just do this all the time, but the diffuse OH people could do it more probably.
Thanks for that, Michael. I think before we go on to Malcolm's talk, I want to mention something. I'm trying to compile. I've got a couple of lists going. I've got some spreadsheets going that I've shared here and there on the Slack. They're also linked on the homepage of the website. And one of them is just codes. So if there's any code like Malpop, I've already signed up Michael for this for Malpop. But if there's any other codes that you have experience using, it doesn't have to be your code. It just has to be something that you'd be willing to help somebody else use. If you could add that to the list, that'd be awesome. I'll put the link in the chat, but like I said, it's also on the website. So, excuse me, my partner made me sick. I'm very annoyed. He had the flu earlier in the week, and I'm just looking at him like, not this week. All right, so off to you, Malcolm.
Right, okay. So I guess I need to try and share something. Is that visible to everybody?
Yes.
Yep.
Okay, so if I try and run it as slideshow. That'll have to do, I think. Is that okay? Okay, so when I went to NARIT, I'd already been working on the very early sort of essays at this code with Sandra back in Manchester, and Kitiani Asanok had a PhD student, Montree Fetcher, who eventually got his PhD, thankfully, on this project. And it took another 3 years to get it right, for various reasons. But in the end, I think we've got a basic code that now does work, and it's written originally for the narrow splitting case, so for something like SIO. But if it works for that, then hopefully I can demonstrate that it'll work for OH as well, though in a sort of very different magnetic field regime, as you probably expect. So so what does it do? So the thing that's really good about it, I guess, is that it'll do arbitrary shapes, so funny shaped clouds, if you like. So that the studies we did took a sort of roughly spherical thing, and then a sort of compressed version of that with conserved volume. So you put an oblate one and a sort of pulled one that looks like a rugby ball or an American football. And there are also some tube models which are made to compare results with sort of 1D models. So if you make the tube very long, then I guess it ought to look like a 1D code in the end. So it's a finite element code. So you build a domain using a Delaunay triangulation, and you then use the shape functions that come from that to discretize what goes on inside the domain. But I should add it's not a differential equation solver in the usual finite element sense. So that is the inversions. There is no term that is a spatial differential of the inversions in there. All that is actually taken out, and what it solves is effectively integral equations in the inversions. And so the inversions will just be in a Zeeman pattern. So you could, for example, take, let's say, the 1665 megahertz OH triplet, or the SIO J equals 1 to 0 triplet. But all that complexity of the rest of the molecule at the moment is just represented through pumping terms. So as far as the molecular sophistication goes, it's pretty poor at the moment. So it's a set style code. So that is the radiation integrals get eliminated analytically effectively, so that the things that you actually solve for are the inversions in the polarized or magnetic transitions that you've got. And the equations end up giving you a set of nonlinear algebraic equations. And that's what you solve for. And the thing that controls how that's done is this orthomin algorithm. More about that later, I guess. So it does measure saturation by doing these integrals, and the results of those integrals are pre-computed saturation coefficients. And so you can just calculate these once at the start of each run, and then they're just in a big array. And it's unfortunately rather memory intensive doing it like that. And I think if I want to make the domains a lot bigger or include a lot more levels, that will have to be sacrificed. And I'll probably only be able to store simpler coefficients that take up less memory per level or per domain node. So the scaling of it roughly is the number of nodes in the domain times the number of magnetic transitions. So obviously, putting in a very realistic model of OH with lots of rotational levels would make it a lot more time intensive. So anyway, once you've got a solution which is the inversion at every node and in every magnetic transition, you can then follow it up with just a cheap formal solution with the known inversions, and you generate spectra and maps. Okay, so this orthomin algorithm, it was originally just a convergence accelerator. So some of you might or might not be familiar with the type accelerator, which you use to you take previous iterates, and it uses a least squares method to improve the convergence. And orthomin originally sort of did that, but it also had a minimization system as well. So it's got orthogonality and minimization, whereas I think the accelerator is just least squares minimization, and it applies these correction coefficients. And the original orthomin, the Vinson paper, it's some sort of geographical thing, like looking for oil or something. But don't use that version. So this Chen and Kai 2001 method, uses its orthomin K, and K is the order, and it's almost always 2 as far as I'm concerned. I've not found using a larger order improves things much. So the great advantage of it over something like Levenberg Marcus is you don't need to calculate this huge Jacobian matrix of the derivatives of your function to get all the gradients. It sort of produces a subset of those, I guess, that it deems to be important. And the other really good thing about that is you don't need to code the function derivatives either. So you only ever have to evaluate your function. So that's those equations that define the inversions. So if so there's a sort of typical convergence in the diagram here. So it starts at around 10 to the minus 5, which is the initial guess for this model, and it then ends up with the target of 10 to the minus 8, which is here in the maximum absolute residual. And every time it sort of goes off on a bit of an odyssey, a restart will happen, and that is meant to use the best estimates, which is sort of not the one recorded here, but it'll pick up the best one and restart from that, and hopefully come back to a good convergence progression. I wish I could say that it's a sort of beautiful black box, but unfortunately, yeah, there are some free parameters that you have to sort of meddle with, and although it is very good, yeah, there are still some problems using it in some cases. So we ran it parallel on OpenMP. So there's a sort of early laptop test up here, which is, well, it shows an improvement. I think there are 12 processors on my laptop. But the better example is the lower one on the Chalawan computer at NARIT in Chiang Mai. So there you can go up to 32 threads, and sort of averaging over all of those doublings, if you double the number of threads, the runtime goes down to 0.563, and if it scaled perfectly, it would be half, of course. So it's a pretty good parallel scaling code, and the main loop that is parallelized is over the nodes of the model. So it can separate the nodes up to a point and run those in parallel. So the orthomin relies on some sort of good initial guesses when the saturation is strong and the equations are quite stiff. So this is just sort of taking one node of the model in this example, and it shows how the inversion progresses with maser depth or saturation on the x-axis. So you've got a pi inversion here, which is not destroyed so heavily as the sigmas. The sigmas are, by the time you reach depth 50, they are below 10%. So everything starts at 1, of course. So the very first run, obviously you don't have a previous solution, and that just has to go as it is, and it's a very low depth, and the error is very small anyway. Then after that, you can use polynomial or rational function or Parde approximant methods to give you an initial guess, and it saves a lot of time if you do that. There are different possible orders. Once you've got a lot of previous solutions, you can run quite high orders, but polynomial 3 and rational function 9 are typically good bets. And so you have to sort of bootstrap this up from a very unsaturated start. So you'd start with just small polynomials up here, maybe go to the rational function 9 when you're in the strongly saturated regime on the right. Right, this will send everyone to sleep. So here are the equations. So it uses a semi-classical model, and it sort of has to do that because you're dealing with something that needs the density matrix, and particularly the off-diagonal elements of that represent sort of coherences between the energy levels. And you therefore use this quantum mechanical density matrix and Maxwell's equations for the radiation. So there are various stages to this. So there's a rotating wave approximation that gets rid of all the oscillations that are actually at the wave frequency. So the electric field things in the top equation here are they're complex amplitudes of the field, not right. All the fast oscillations have gone. So that gets solved analytically by a method by Landi di Innocenti, and the matrix solution is sort of at the bottom here. So it's a sort of like a series solution with iterated matrices, and that allows you to get rid of the electric field from the off-diagonal elements, which is the S thing, and then that can also be eliminated from the equation in the delta, which is the inversion. So what you've finally got is a pumping term here. So P1. So P is your level in the MJ sense. So you sort of got -1, 0, and 1 for your sigmas and your pi, and then there's a loss rate gamma. W is a solid angle weighting. D's are your dipoles, and they dot onto these complex amplitude vectors for the electric field. And so you've eliminated the off-diagonal elements and you've eliminated the electric field amplitudes. Right, so once you've done the rotating wave approximation, it's all put in the Fourier domain. So you've got the idea of channels within what. So there's obviously a finite sampling time in which, in a sense, there's no more time variable within that. And you solve for the inversions, which is the sort of biggest box here. And very importantly, you don't use the Stokes parameters in here. Do it all at the electric field level, because it's a lot simpler. Because the problem with Stokes parameters is that they're sort of in they're a sort of observer-based set of variables, and it's sort of much easier to just deal with electric field vectors. So the Stokes parameters only appear in the formal solutions at the end. Right. Yeah, it's a rather old school code. So Moshe Elitzer wrote his in Fortran, and sadly maybe this is in Fortran as well. So there's no Python, not even any C. There are sort of 4 sections in this parameter file. Some integers, which mainly are control parameters, some logical flags, real numbers that specify most of the physical things, and then strings at the end, which tell you, which directory to put the results in, and so on. So in addition to this parameter file, you also need things that tell you what the domain is doing. So there's a node table. So for each node, it just tells you the position in X, Y, Z Cartesian coordinates. The element table tells you which numbered nodes each finite element is built out of. So it gives you a list of 4 nodes and 4 neighboring elements. And if the face of the tetrahedron is external, then that gives you a neighbor number of 0. And then each element and each node has a shape function, and that has 4 coefficients, and those will all appear in the shape function file. And then finally, there's a physical conditions file that, well, in particular, it specifies the magnetic field, some densities and so on. On we go. So tube domains were the things that we sort of studied first to try and compare things with 1D models. So the nodes in this case sit on the surface of this cylinder. So length to radius ratio. We used 3 different ones, and most of the results are for the longest, thinnest one, where L over R is 10. And then there are loads of rays that come from a sort of celestial sphere source, and those then impinge on every node of the target. So you're within the domain, you actually have to obviously integrate the ray through the material, which is magnetized. So the long axis is generally Z, and then the magnetic field is placed at some angle to Z. So in this diagram down here, it would be at about I don't know, 80 degrees maybe. And the rays all have their own sort of independent axis system, so that you can make that polarized if you wish by specifying a different complex amplitude for the rays' local X and Y axes. Right, okay, to carry on. So I think in the weak splitting case, that certain results had to be reproduced to say it agrees with 1D models, at least approximately. So the system is something like MSIO molecule in the J equals 1 to 0 case, so sort of 43 gigahertz model. We used 5 Gauss at various angles. So the sampling here is every 5 degrees. And the things that we sort of had to reproduce is the Q over I sign change at the Van Vleck angle, which is just under 55 degrees. So the blue line here, which is the linear polarization Stokes Q, it does pretty much change sign at that angle. U has to be about 0 because we're using the sort of vertical horizontal cross. V over I has to be a function that starts at maybe a sort of few percent and decays therefore to 0 when it's when the angle's about 90 degrees, which it does within errors anyway. And the electric vector position angle also has to flip at the Van Vleck angle, so that's the red line, and it does. And the amount of circular polarization you've got as measured by, say, the peak value in the spectrum should be proportional to the magnetic field, as long as the splitting is not too great, and that isn't shown on this diagram, but it does do that. And that's now published in this paper of this year in Monthly Notices. Right, so, okay. If we want to convert it to study OH, we can do that probably on the main lines, because they again have this simple structure, which is at worst a pair of sigma transitions and a central unshifted pi. So in the sorry, 16, I think I mean 1665 megahertz actually. Then the 2 delta V, which is the splitting between the sigmas, is that figure there, 0.589 B in milligauss kilometers per second. So to compare that with SIO, obviously it's much smaller. In SIO J1 to 0, V1, it's 1.64 10 to the minus 6 for this number instead. Okay. So what field for OH will give the same splitting as 5 Gauss in SIO? And it turns out, well, combining those equations there, to be 13.9 microgauss in OH. So something I'm not really sure about is, you know, are there some sources where OH is in this narrow splitting regime where the field is perhaps anomalously low? Possibly some of the water fountain sources might have OH in the narrow splitting regime. Maybe good for discussion later. So to do this with some models, just sort of multiplied up the splitting to see what happens, and it does seem to work nicely. So this is a ×2 splitting, and it just doubles each time, and you can see that the Stokes V, which starts as a sort of few percent down here, becomes stronger with each doubling, and somewhere between the 32 and 64 cases, it hits 100% at the peak, and you can then say probably with the 64 case that it is now in the wide splitting regime. So you've got a Stokes V signal that would be 100% circularly polarized opposite hands as you switch across the spectrum. And note that the number of channels being used here is actually rising a lot. So it's not all the same width presented here by any means. You can also look at that in ratio spectra, so everything ratioed to Stokes I. And again, you see the effect on Stokes V. And it actually hits 100% in the 32, but it's not 100% at the peak there. And that doesn't finally happen till you're in the 64. Right. What else have we got? Yeah, so I'm still sort of running jobs for the magnetic field in the sky plane at that same high splitting 64, and I used the highest depth that I got to, but it's actually lower than the B parallel figures that I've just shown you, and the Stokes I is still at this point in a single line shape, but you can see that Stokes Q is breaking into this triplet, and it's easier to see in the ratio spectrum. And what I expect to happen as the splitting is increased further is that Stokes Q will actually go negative in the middle, and then you've got your triplet, and the Stokes I will eventually split into 3 parts. Yeah, so one reason for trying to do this is to measure Stokes V. Measure the magnetic field from Stokes V, looking at some sort of modeled relation. So this curve is for one saturated depth, right? So the maser depth is 50, and the magnetic field is always towards the observer in this figure here. So your B parallel, your parallel component is the same as the overall magnetic field strength. And you can see that there's actually quite a good linear relation up to a Stokes V fraction of about 0.6. So that would be the brightest bit of Stokes I in the Stokes V in the spectrum. So up to about 0.6, you can just say that the polarization that you observe in V in circular is pretty much linearly related to the magnetic field. So if you know the equation of the line, you can derive your field. So on the 1665 megahertz scale, so B is in sort of micro Gauss here, so using it as an OH model, the narrow splitting regime ends at about 300 micro Gauss, where the maximum V hits 100%, and then essentially you're moving into the regime where you've got two independently propagating circularly polarized lines with opposite hands. Yeah. So why might I want to do this sort of modeling? So if you look at the energy densities in these sort of star forming regions, the thermal gas is pretty weak. So 1.4 10 to the minus 12 joules per cubic meter multiplied by T in units of 100K or n in units of 10 to the 12 H2 per cubic meter. Microturbulence, because it's probably going to be supersonic, gives you more than that, about 2 × 10⁻⁹ joules per cubic meter, multiplied by v² in kilometers per second, and this number density again. The magnetic field, though, gives you even more, 4 × 10⁻⁹ v² in milligauss. And we certainly know that there are fields of quite a few milligauss available. So the magnetic field is likely to be dynamically important, if not actually the dominant controller of the dynamics. And the often used relation B proportional to density to the half relies on things, ions being frozen in, so bound to the magnetic field. So that means that motion perpendicular to the field lines is probably difficult. So as a cloud relaxes, it's almost certainly going to elongate. So it become a sort of prolate object, elongated along the magnetic field lines. So the idea here is maybe that you form your clouds as a sort of maybe a pseudo-spherical object, not knowing any different really. So viewed with the field towards us, it looks like that. It looks a bit different with the field in the sky plane, but so now you're looking across the field. So with the field towards us, you would expect to see circular polarization in Zeeman doublets, which is generally what we do see. And if the field's in the plane of the sky, we'd expect linear polarization in triplets. So a pi component aligned with the magnetic field and 2 sigmas at 90 degrees to the field direction. Now, if those then relax over sort of years, decades, or even centuries, then the face-on view sort of ends up looking fairly similar, but the cloud behind it is now longer and lower density, but you're still amplifying through roughly the same amount of material. So you'd still expect to see circular doublets, maybe a bit weaker, but the relaxation doesn't do a lot to you if you're looking down the field lines. But if you're looking across, that elongation makes the thing sort of optically very thin, because the clouds now spread over a long distance in the plane of the sky, and you probably won't see it because the amplification will be very low. So this would be hard to observe. And that may explain why you only see about, I think is it 18% of triplets or something. So if you observe a triplet, you'd probably be seeing, well, in this model or this idea only really, you'd be seeing a young cloud. So this is just sort of for discussion really. Looked at that. So what developments should go into this? So certainly it should be able to address more complicated Zeeman patterns. That's not a terribly difficult thing to do, actually. And it won't cost an awful lot computationally. You probably want to vary the magnitude of the B field within the domain. It'll already do angles, so you can change the field direction within the domain, but not the strength. You'd want to include the so-called type 2 off-diagonal density matrix elements. So that's the ones that are in, that will relate to the transitions in blue here. So it's transitions that just change MJ, but they don't change J or F in OH. So that they're purely within the magnetic substructure. Now, what those do is when the stimulated emission rate gets larger than the Zeeman splitting itself, these things start to become strong. They mix the substates up, and they take away the nice status of the magnetic field direction as a good quantization axis, and instead it starts to swing towards the radiation propagation axis in a 1D model. But of course, in a 3D model, radiation's going everywhere, so you can't sort of say it's stuck to the radiation axis. But you can still include these off-diagonal elements between the magnetic substructure, and that complicates things quite a lot. It would be nice to use much larger domains, probably having to sacrifice those once-only saturation coefficients. Partial velocity redistribution would be nice, but memory expensive, because instead of just having one inversion for each transition, you would now have one inversion for a whole load of velocity bins. So a lot more coefficients need to be calculated. And also, again, given what Michael was talking about, it would be nice to actually have more than just one Zeeman pattern, but all the Zeeman patterns that would fit in if you like, a proper OH model, which it doesn't do at the moment. So that's probably the sort of desiderata for improving the model. I guess there's just one more slide that people might be interested in, related to the results of the tube domains, and that sort of, well, it shows you the other shapes of domains we tried in the 2025 paper, the oblate, sort of pseudo-spherical and prolate, and this is quite strongly saturated. You can see that there's an unsaturated core and saturated ends, for example, in the prolate model, or saturated edges in the oblate one. And then we got like maps and spectra. And one 3D effect is that you can actually get something like 100% Stokes Q without any recourse to asymmetric pumping, just geometrical. And there's also an effect in the oblate case. So the color bar here is the ratio of the inversions of the pi component to the combined sigmas. And you can see that if you viewed this thing as you sort of went round the outside, every time it crosses one of these diagonal lines, you would actually see a flip in the sign of Stokes Q, and that is a 3D effect, and it's sort of not totally expected, and it's based on differential saturation of different paths through the object. Right, I think that's all I'm going to say for the moment. I'm sure there are lots of questions. Mm.
Thanks a lot for that, Malcolm. I'm gonna
Right.
keep muting you. So gosh, there's a lot there. Does anybody have any questions for Malcolm?
Hello. Well, I have a comment, Malcolm, actually, not a question. Thanks. Nice talk and really interesting results there on that paper. I'll be happy to check it out after the presentation. But my comment is actually just to thank you because it turns out I have your book here. It's one of the favorite books that I recommend to my students. So
Oh, well,
it's really
awesome.
nice.
Thank you.
Yeah, great service to the community.
Buy me a few beers. Yeah.
That's right. That's the minimum should have been that, yes.
Michael? Yeah.
Yeah, thanks a lot. This was really interesting. Yeah, so I was just wondering, like how, okay, I don't know how to put this, but so the could you use, so would so I guess the comparison is so the measurement would still give you I don't know, a plane of the sky, so one line of sight measurement of the Zeeman splitting or the or yeah, that is there any way you would think that, I don't know, with some of the 3D reconstructions of the of the dust density field, or maybe even at some point the magnetic field, this could do you see any synergies or yeah, with your models? It's a bit of a random question, but yeah.
We can't hear you, Michael. Oh, sorry, Malcolm.
Right. I could just take some of those ray sites and make them stronger than the rest of the background. And that would simulate having some, sort of hotter dust or some background that is stronger than the basic value. So as for modeling magnetic field structures, so I think that's sort of what I want to do. Just sort of looking at different shaped clouds, assuming that they evolve somehow by elongating along the field lines, and see if that gives you the right sort of statistics for the fraction of triplets. I mean, that's just the sort of the idea I had.
Okay, thanks.
I had a question. Sorry. So I've found a lot of times when I'm trying to model OH in more diffuse regimes than in high mass star forming regions with masers, that the line widths that we observe are on the order of higher than a kilometer per second. But I find that with most of the modeling codes, the line overlap disables a lot of the inversions at line widths wider than that. I was wondering if that's something that happens in your code as well. But also kind of along those same lines, like how far down in column density would you say that your models would be applicable? And yet you're still muted.
I don't know, it keeps going on to mute. There must be some sort of lower limit, I guess, but I can't think of a, why there should be a lower limit offhand. I mean, I suppose the advantage of this type of code is that I could just sort of change the pumping terms to be weaker and weaker. I'm maybe not getting the gist of the question properly.
Oh no, it's okay.
Oh, no, it's okay.
I was more worried. Sorry, I mute you again. I was more wondering about, since this seems to for more like forming mesa regions and that, if it's still applicable if we're working in a much less dense domain.
Well,
Sorry,
I don't see why not. I don't see why not.
Efficient.
Right. I say I don't. I mean, if you try to build sort of a model of a diffuse cloud that's much bigger and much less dense, I don't see why it wouldn't work. I mean, there might be some reason that there's a lower limit on the density or the column density, but I can't think of why there should be. Really.
Could you maybe tell more about the physical conditions that go into the model, like in terms of the actual parameters of the cloud, like the size, the number, density, and that kind of stuff?
Well, so because the size is all sort of scaled to one. But yeah, you can work out what you can work out what the real size is, but you can scale everything, so you really just have this you just have this depth, which gives you a range of possible saturation on it. I mean, how large are the clouds you want to model? I mean, they're sort of parsec size, right?
Yeah, some of them have be multiple parsecs, because after a certain point you lose the velocity coherence, so they would end up either being separated out into different components in the spectra. So you'd be able to tell that they're different, and could therefore model them separately. But yeah, parsec or so, maybe up to 10, but probably not quite that big.
Right. So okay. So something I should mention. So there's no independent velocity field inside the domain at the moment, right? So you would have to program that in somehow, and that somehow think that will be horrible. But you could vary them. You can vary the magnetic field within the domain. So the direction of it at the moment, anyway. But say if you've got a sort of parsec size cloud, but your density is down at 1/10,000th of what it is in the star forming region or something like that, then you can probably still run the model, get a solution.
I was interested in what you were saying about the cloud lengthening. Sorry, I keep muting you. There's really bad echo.
Yes. Okay.
Yeah. Hold on. So when you were saying that there was this lengthening along the magnetic field lines, could you comment maybe on the time scales of that and the distance scales of that?
Well, I think that just comparing it with some other work that I did for maser flares, with the sort of typical densities and sound speed and so on, it would take somewhere between a few years to a few centuries, depending on sort of how big the cloud is. So I mean, sound at 1 kilometer a second, it takes about 5 years to cover an AU, I think. But if you're talking about parsec size clouds, then it's loads longer, obviously.
Simon?
Yes, so I have a question related to the this result. It's kind of interesting, the 3D effects in oblate model that you were mentioning. I was wondering if you have given any thought on whether this will be detectable in BLBI observations of masers where they may be resolved, and then you can explore different polarization signals in the resolved maser.
Yeah, if you had some idea of what the cloud shape was, then yeah, it would affect the statistics of the amount of Stokes Q and the sign of Stokes Q that you would expect to see.
Would it be possible to extract somehow the geometry of the cloud based on the observations?
Well, I mean, the suggestion that I'm making is that they're generally sort of prolate objects, and their sort of long axis is generally towards you, to give you the big gain lengths. So if that's actually the case, you wouldn't see that effect, in fact, because that appeared in the oblate models, or at least it was very strong in the oblate models. So maybe it would be difficult unless there's a convincing argument for shock flattened clouds or something like that.
Interesting, something to explore with the data. Right?
Yeah, I'm not sure how much VLBI could tell you about the cloud shape. Might have to talk to Anita Richards about that.
Do you have any more questions?
So there's something on I'm just sort of looking at the chat.
That was from
something about editing the
Malcom,
input file or something. I mean, there's a script that does that. So if that's aimed at me, anyway, I don't know.
Oh no, that was for Malpop. I think it has a similar input file, but we were trying to discuss best pipeline practices, I guess.
Yeah, I mean, it's obviously right. I mean, with my code as well, that thing does have to be edited for each model, but there's a script that can do that, so it can just run any number of similar models, I guess.
Do we have any more questions? Well, if not, then I'd like to hold on.
Yeah, there's just one thing I was going to ask. Does anyone actually know of any?
Sorry, you may have noticed in the Slack that I mentioned that some of our session times on Friday are available for any kind of planning of new projects. Something that I was hoping to take one of those time slots for is trying to come up with some way of making these codes that will do this kind of, you know, sophisticated molecular excitation modeling, to try and make them a little bit more accessible for wider users. I don't know if that would be something like Radx is a really nice tool that people are able to use, but I don't think it's able to do OH really well enough for our purposes. So maybe it would be something like that. But I was wondering if anybody would be interested in being involved in something like that. And if so, then I can assign a breakout room to that on Friday.
Yeah, I would be interested for sure.
Yeah, cool. Two's enough.
So yeah, there was just one question I wanted to ask. Does anyone know of any sources where OH is definitely in narrow splitting, where it looks like the sigma transitions are superimposed pretty much, and the splitting is very small.
You mean in
compared to the Doppler width?
Like a narrow split, circular polarization.
Yeah, where it's sort of almost too small to measure.
I mean, probably.
Isn't that the level of splitting that happens in like the old Butcher papers where they're measuring the magnetic fields in like H1 in molecular clouds?
Yeah, I think that would be the same regime. Yeah,
That would be the narrow regime, not narrow regime, because they're always hard to measure. I know that.
Right.
I think what might be more common, at least I know for my data, what's more common is that there's quite a lot of features in the spectra, right? So it's a bit ambiguous of which one is right and left, which one is which. So it's a little bit hard to tell exactly how much the splitting is. But I
take that point. Yeah, there are a lot of features, that don't fit nicely into Zeeman patterns. Yeah, sure. Yeah.
So yeah, it's hard to tell. It's something that is its partner is actually over here, but it ends up looking like it's next to this one. But I suppose, and this might be something that other people could answer, because it's more of a observational and database sort of question. I was wondering how people treat those kind of spectra. If you do anything along, magnetic field lines along the line of sight towards regions where there's more than one spectral feature where it can be a bit ambiguous. I wonder if making some kind of assumption that the magnetic field strength would be relatively constant, if that's valid, because that would be a nice nice trick. I wonder if anybody has experience of trying to unravel that problem.
Yeah, I mean, you'd have to use some sort of multi-cloud model, right, to sample different bits of the field structure. Is that right?
Yeah, I'm guessing because when you're looking at a spectrum and you're looking at the right and left hand circular polarization and you're playing that game of trying to match up right and left, it can be very ambiguous because you can't match them up by strength. They all have the same width, so that doesn't even matter. It just becomes a really tricky process. There are some regions like I've tried to do it with things that like vary together because I have a lot of variable masers. But then usually, they're all going up and down at the same time. So it becomes really, really difficult to have a model of which pair is which so that you can then start to measure the magnetic field strength. But I mean, if I could make an assumption that I would expect the magnetic field strength to be relatively constant throughout say a region that spans like 15 or 20 kilometers per second, but lots of individual spectral features, so lots of different little clouds. I mean, I don't know if the source of these magnetic fields is that broadly spread out for that even to be a reasonable assumption.
Perhaps a comment there. So what about higher angular resolution? Going back to the idea of BLBI, observations of the individual masers. So at least you can separate some of them.
Oh no,
Especially-
you're absolutely right. You're absolutely right. But then, yeah, and that is an avenue that I've gone down. But with my monitoring project where I'm monitoring like 50 or 60 different masers to be able to get the long baseline time to be able to sort these out, and they tend to vary on. Oh, some of them have cataclysmic events which can completely change their spectra. So then all those observations go out the window. But no, that's a very good point, and that's very right actually.
Yeah, I guess as a minimum, it could be an epoch where you can compare, like you can time the observations with BLBI and single dish, right? So you can then basically have an idea of what is really happening with your single dish spectra, right? With respect to the high angular resolution, and then decide whether your different methods are valid or not, type of thing.
That's a very good point. Hmm. Hmm. Right, do we have any more questions for either Malcolm or Michael or any other discussion points? All right, if not, well then let's thank our speakers again. Thank you, Michael, and thank you, Malcolm, for really interesting talks. And hopefully we can keep some conversation going on Slack if you have any further questions or you come up with anything. And also please have a look at that list of codes. It might only have one or two things on it at the moment, but that's all right. And yeah, I'll schedule a meeting time on Friday and we'll see if we can get everybody that's interested into that one. Because that'd be cool to see how we can make this a little bit more widely available for people. So thanks a lot, guys, and I'll see you in the next session.
Hi, everyone. Thank you.
Thank you.